Basic topology of C. A circle in the complex plane is the set of all points that are at a fixed distance from a fixed point. The fixed distance is called the radius of the circle, and the fixed point is called the center of the circle. If a circle has radius r greater than 0 and center c equals a plus bi, then any point z equals x plus yi on the circle must satisfy absolute z minus c equals r, or equivalently, x minus a squared plus y minus b squared is equal to r squared. Note, the equation absolute z minus c equals r says the distance between c and c is equal to r. In other words, the distance between any point on the circle and the center of the circle is equal to the radius of the circle. Let's look at an example. The circle with equation absolute z plus 2 minus I equals 2, or equivalently, the absolute value of z minus negative 2 plus I equals 2, has center c equals negative 2 plus I, and radius r equals 2. Here we see a picture of this circle in the complex plane. Let's try an exercise. Find the center and radius of the circle with the given equation. Now's a good time to pause this video, try this exercise yourself, and then resume the video to check your answers against mine. First one, absolute z minus I is equal to 5. The center is I, the radius is 5. Absolute z minus 2 minus 3i equals 11. The center is 2 minus 3i, the radius is 11. Absolute z plus 3 plus 2i is equal to 2. The center is negative 3 minus 2i, the radius is 2. X squared plus y squared equals 9. The center is 0, the radius is 3. X minus 3 squared plus y plus 1 squared is equal to 17. The center is 3 minus I, and the radius is the square root of 17. Note, if x and a are real numbers, then the equation absolute x minus a is equal to r is equivalent to the statement x minus a equals r, or x minus a equals negative r. Or equivalently, x equals a plus r, or x equals a minus r. So the real valued version of a circle is 2 points that are equidistant from the center of the circle. Let's look at an example. The equation absolute x minus 1 equals 2 is equivalent to x equals 1 plus 2 equals 3, or x equals 1 minus 2 equals negative 1. In other words, there are exactly 2 real numbers that are at a distance of 2 from 1. These 2 numbers are 3 and negative 1. Here we see a picture of the real line with the center 1 and the 2 points negative 1 and 3 that are each at a distance of 2 from 1. An open disk in C consists of all the points in the interior of a circle. If A is the center of the open disk and R is the radius of the open disk, then any point Z inside the disk satisfies absolute value of Z minus A is less than R. N sub R of A is equal to the set of complex numbers Z such that the absolute value of Z minus A is less than R. This is also called the R neighborhood of A. Let's look at an example. N sub 2 of negative 2 plus I, or the 2 neighborhood of negative 2 plus I, is equal to the set of complex numbers Z such that Z minus negative 2 plus I is less than 2, or equivalently, the set of complex numbers Z such that Z plus 2 minus I in absolute values is less than 2. This is the 2 neighborhood of negative 2 plus I. It consists of all points inside the circle absolute Z plus 2 minus I is equal to 2. Here we see a picture of the 2 neighborhood of negative 2 plus I. Notice that we shade the circle to indicate that the whole interior is included, and we use dashed lines around the boundary to indicate that the boundary is not included. The definitions of open disk and R neighborhood of A also make sense in R, but the geometry looks a bit different. An open disk in R is simply an open interval. If X and A are real numbers, then we have X in n sub R of A, if and only if the absolute value of X minus A is less than R, if and only if the square root of the square of X minus A is less than R, if and only if 0 less than or equal to the square of X minus A is less than R squared, if and only if X minus A is between negative R and R, if and only if X is between A minus R and A plus R, if and only if X is in the open interval A minus R, A plus R. So in R, an R neighborhood of A is the open interval n sub R of A equals A minus R, A plus R. Notice that the length or diameter of this interval is 2R. Let's look at an example. N sub 2 of 1, or the 2 neighborhood of 1, is equal to the open interval 1 minus 2, 1 plus 2, or equivalently the open interval negative 1, 3. Here we see a picture of this open interval drawn on the real line. Let's try another exercise. Find the center and radius of each of the following open disks. Now's a good time to pause the video, try this exercise yourself, and then resume the video to check your answers. N sub 4 of 7 minus 3i. The center is 7 minus 3i. The radius is 4. The set of complex numbers z such that the absolute value of z minus 1 plus I is less than 6. The center is 1 minus I, and the radius is 6. The set of complex numbers x plus yi such that x plus 2 squared plus y minus 1 squared is less than 3. The center is negative 2 plus I, and the radius is the square root of 3. A closed disk is the interior of a circle together with the circle itself. In other words, the boundary is included. If A is the center of the closed disk and R is the radius of the closed disk, then any point Z inside the closed disk satisfies the absolute value of Z minus A is less than or equal to R. Let's look at an example. N sub 2 of negative 2 plus I with a bar over it. We use the bar to indicate it's the closed disk as opposed to the open disk. This is equal to the set of complex numbers z such that the absolute value of z minus negative 2 plus I is less than or equal to 2. Or equivalently, the set of complex numbers z such that absolute z plus 2 minus I is less than or equal to 2. This is the closed disk with center negative 2 plus I and radius 2. It consists of all points on or inside the circle, absolute value of z plus 2 minus I equals 2. Here we see a picture of this closed disk. Notice that the disk is shaded to indicate that the interior is included. And this time we have a solid border around the boundary to indicate that the boundary is included. Just like an open disk in R is an open interval, a closed disk in R is a closed interval. Let's try another exercise. Use set builder notation to describe the closed disk with the given center and radius. Go ahead once again, pause the video, try this exercise yourself, and then resume the video to check your answers against mine. Okay, the first one, center equals 3i, radius equals 1. The set of complex numbers z such that the absolute value of z minus 3i is less than or equal to 1, or the set of complex numbers x plus yi such that x squared plus y minus 3 squared is less than or equal to 1. Center equals 8 plus I, radius equals the square root of 2. The set of complex numbers z such that the absolute value of z minus 8 plus I is less than or equal to root 2, or the set of complex numbers x plus yi such that x minus 8 squared plus y minus 1 squared is less than or equal to 2. Center equals -1 plus 2i, radius equals 1.5. The set of complex numbers z such the absolute value of z minus -1 plus 2i is less than or equal to 1.5, or the set of complex numbers x plus yi such that x plus 1 squared plus y minus 2 squared is less than or equal to 2.25. A punctured open disk consists of all the points in the interior of a circle except for the center of the circle. If A is the center of the punctured open disk and R is the radius of the open disk, then any point Z inside the punctured disk satisfies absolute value of Z minus A is less than R and Z is not equal to A. Note that Z not equal to A is equivalent to Z minus A not equal to 0. In turn, this is equivalent to the absolute value of Z minus A not equal to 0. Since absolute value of Z minus A must be non-negative, the absolute value of Z minus A not equal to 0 is equivalent to the absolute value of Z minus A greater than 0, or 0 less than absolute value of Z minus A. Therefore, a punctured open disk with centered A and radius R consists of all points Z that satisfy 0 less than absolute Z minus A less than R. N sub R dot of A is equal to the set of complex numbers Z such that 0 less than absolute value of Z minus A less than R is also called a deleted R neighborhood of A. Let's look at an example. The deleted 2 neighborhood of -2 plus I is n sub 2 dot of -2 plus I equals the set of complex numbers Z such that 0 less than absolute value of Z minus -2 plus I less than 2, or equivalently the set of complex numbers Z such that 0 less than absolute Z plus 2 minus I less than 2. It consists of all points inside the circle, absolute Z plus 2 minus I equals 2, except for -2 plus I. Okay, here's a picture of the deleted 2 neighborhood of -2 plus I. You can see we shade everything inside the disk, but we leave a hole at -2 plus I to indicate it's not included. And we use dashed around the boundary to indicate that the boundary is not included. In R, we have n sub R dot of A equals the open interval A minus R, A plus R, minus the set consisting of A, which is the union of the two open intervals A minus RA and A plus R. This is the open interval centered at A of length or diameter 2R with A removed. Example, n sub 2 dot of 1 is the open interval -1, 3 minus the set consisting of just 1, which is -1, 1, union 1, 3. And here we see a picture of this on the real line. It's the open interval from -1 to 3 with 1 removed. A subset X of C is said to be open if for every complex number Z in X, there's an open disk D with Z in D and D a subset of X. In words, a set is open in C if every point in the set has some space all around it inside the set. If you think of each point in the set as an animal, then each animal in the set should be able to move a little in any direction it chooses without leaving the set. Another way to think of this is that no number is right on the edge or the boundary of the set about to fall out of the set. Let's look at some examples. Every open disk D is an open set. To see this, simply observe that if Z is in D, then D itself is an open disk with Z in D and D a subset of D. A closed disk is not an open set because it contains its boundary. If we take any subset of a disk that contains any points on the bounding circle, then that set will not be open. The empty set and the set of complex numbers are both open. Let's try another exercise. Determine if each of the following sets is open in C. Now's a good time once again to pause the video, try this exercise yourself, and then resume the video to check your answers against mine. Okay, let's go through the answers. The first one is open. The second one is not open. The third one is open. The fourth one, not open. The fifth one is open. The sixth one is open. The seventh one is open. And the eighth one also open. A subset X of C is said to be closed if C minus X is open. C minus X is called the complement of X in C, or simply the complement of X. It consists of all complex numbers not in X. Let's look at an example. The closed unit disk D equals the set of complex numbers Z such that absolute Z is less than or equal to 1 is closed in C because its complement in C is C minus D, which is the set of all complex numbers Z such that absolute Z greater than 1, which is open.